Today we're going to talk about logarithms and their derivatives. So to remind you what a logarithm is, it is the inverse of an exponential function. So we're going to graph 2 to the x, and then we're going to graph its inverse, which would be log base 2. So I'm going to fill in this table of values. So 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8. 2 to the negative 1 would be 1 over 2, so this is 1/2, 1/4, 1/8. So we graph this, 0, 1, 1's at 2, 2's at 4, 3's at 8. 1, 2, 1, 2, 3, 4. 2 is at 8. And then backtrack, it just gets closer to that axis. So the domain is all reals. The range is y is greater than 0. The limit as x goes to infinity of 2 to the x is infinity. The limit as x goes to negative infinity is 0. For the graph of the inverse, I'm going to take these and switch the x and y. So we're going to have 1/8 negative 3, 1/4 negative 2, 1/2 negative 1, 1, 0, 2, 1, 4, 2, and 3, 8. 8 to 3, sorry. Okay, and then we'll graph those here. So just like exponentials always cross at 0, 1, logarithms always have a point at 1, 0. The next point is going to be 2, 1, 4 is at 2, and 8 is at 3. Going this direction, 1/2 is at negative 1, and so on. So this graph is going to look like that. So that's the graph of log base 2, but all logarithms will essentially look like that with different slopes. The domain is x is greater than 0. We cannot take the log of a negative number. The range, however, is all reals. As x goes to infinity, this will go to infinity. As x goes to 0 from the positive side, it goes to negative infinity. Logs can have any base you want, but there's two that we use more than others: common logs and natural logs. Common log is log base 10. When it's log base 10 or a common log, we just don't write the 10. Log x means log base 10. A natural logarithm, which we will use primarily in here, is log base e of x, which is ln of x. So logarithms allow us to do different things because they behave differently than a lot of other functions. So some properties. One property is that log base b of b is always going to be 1, because this is essentially saying b to what power would equal b, and that's always going to be 1. Log base b of 1 is always going to be 0, because b to what power equals 0? Well, b to what power equals 1, always going to be 0. Then there's some other properties of logs. The product property. If you have log base b of a product, that can be split up into log base b of c plus log base b of d. If you have a quotient, it's the same but with subtraction. So log base b of c minus log base b of d. And lastly, if you have a power, so log base b, let's say c to some power, I can multiply down that power to get that new function. All right, so let's simplify. Understanding log notation. What this is saying is 10 to what power equals 100? Well, 10 squared would equal 100. So log base 10 of 100 is going to be 2. Natural log of v squared, natural log of e to the anything, these are inverses of each other. So they cancel each other out. So it's just going to be 2. Natural log of e to the cosine is just cosine. There's a couple different ways we can handle d. In the notes, I did it one way. I'm going to show you a different way here in the video. So log base 3 of 9 to the x plus 4. So I can rewrite this as log base 3 of 3 squared. And then the log base 3 power cancels. So then this is 2 times x plus 4, which is 2x plus 8. In the notes, what I did is I took this, multiplied it down, evaluated log base 3 of 9, which is 2, and then multiplied that way. Okay, using the properties, log base 2 of 32 minus log base 2 of 8 is equal to log base 2 of 32 divided by 8, which is log base 2 of 4. So 2 to what power equals 4? 2. Here we have log base 2 of 8 times 4. So log base 2 of 32. So 2 to what power is 32? That answer is 5. Okay, let's compare these two. So log 2 of 4, what power would we raise 2 by to get 4? That answer is still 2. Log base 4 of 2, what would we have to raise 4 by to get 2? Well, the square root of 4 is 2, so the power we would raise it to is 1/2. And what's that relationship? They are reciprocals. Here, I can multiply down the 1/2, so negative 1 times log 2 of 4. So that's negative 1 times 2, or a negative 2. So now we're going to find what the derivative of log base a is. We're also going to find the derivative of natural log. And I'm actually going to start with that one. To do that, this derivation, I'm going to sneak ahead a little bit. Next time we're going to talk about exponentials, and we'll learn this rule. But the derivative of e to the x is e to the x. And we'll get into that next class. But for right now, we're going to use that fact to derive our derivative of natural log and log base a. So first, natural log. So I'm going to raise each power by e. So e to the y equals e to the natural log of x. So now e to the y is equal to just x. Now I'm going to take the derivative of each of those. So the derivative of y, e to the y, is e to the y times, this is going to be an implicit derivative, dy dx, equals derivative of x is 1. So solving for dy dx, we get 1 over e to the y. We don't want it in terms of y, we want it in terms of x. So this is going to equal 1 over e, y equals natural log of x. And e to the natural log of x is x. So the derivative of natural log of x is a surprising 1 over x. Now we can find the derivative of other bases. So y equals log base a of x. I can use what's called the change of base formula and rewrite it as natural log of x over natural log of a. You can use any base, but I'm going to use natural log since we know what its derivative is. So this is the same as 1 over natural log of a times the natural log of x. So now if I take that derivative, this is going to be 1 over natural log of a times the derivative of natural log of x, which is x. So this derivative ends up being 1 over x natural log of a. So the derivative of log base a of x equals 1 over x natural log a. So 2 more derivatives to add to our derivative list. Derivative of natural log of x is 1 over x. Derivative of log base b, or base a, of x is 1 over x natural log of a. So you want to make note cards on those to help you out. So from here on out, now we just have 2 more derivatives we can use. So here we're going to use the chain rule. So this is going to be 1 over x, which in this case is 4x, times the derivative of 4x, which is 4. Well, if I simplify that, I come back to 1 over x. Again, chain rule. So this is going to be 1 over cosine of x times the derivative of cosine, which is a negative sine of x. I am going to go ahead and simplify this one. So this would be negative sine of x over cosine of x. So this is a negative tangent of x. So looking ahead to when we're going to be doing more antiderivatives, the antiderivative of tangent is going to look something like that. Cosine of natural log, we're going to have negative sine natural log of x times the derivative of the inside, 1 over x. Here we have a product. So my derivative is going to be the derivative of cosine times natural log plus the derivative of natural log times cosine, and then just evaluate. So y prime is going to be negative sine x natural log x plus 1 over x cosine of x. Now at first glance it looks like, hey, we probably need to do a quotient rule for this one, a chain rule followed by a quotient rule. But logarithms have some advantages of their properties. So I can actually rewrite this as the natural log of x plus 3 minus the natural log of x squared minus 1, which makes this derivative a whole lot easier than trying to do the quotient rule with this whole thing. So this is going to be 1 over x plus 3 times the derivative of x plus 3, which is just 1, minus 1 over x squared minus 1 times the derivative of x squared minus 1, which is 2x. So with logs, just always keep in the back of your head that we can use the properties to make our lives a little bit easier. Another chain rule. So y prime, the derivative of the square root is 1 over 2 root 1 plus natural log squared x. Okay, times the derivative of the inside, which is going to be 1 plus the natural log squared. Derivative of 1 is 0. This is going to be another chain rule. So this is going to be 2 times the natural log of x times the derivative of natural log, which is 1 over x. And another product. So y prime equals x cubed plus 1 prime natural log x squared x cubed plus 1 cubed plus cubed prime. So when we get to that, we're going to have a lot of chain. But here, so this derivative is 3x squared. This derivative, we have three functions on the outside. Oh, I apologize. On the outside, we have the 3, power 3, then middle's natural log, then the inside is that. So our first is going to be 3 ln x cubed plus 1 squared times, natural log is our next one, 1 over x cubed plus 1. Then the derivative of x cubed plus 1 is 3x squared. And we will multiply that by x cubed plus 1. Next we have a quotient. So y prime, derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. So natural log is 1 over x. Derivative of 1 plus natural log of x is 1 over x. All over 1 plus natural log of x squared. Okay, here we don't have the derivative of natural log, we have the derivative of log base 2. So this is going to be 1 over x, which in this case is 1 over x squared, times the natural log of 2, times the derivative of 1 over x squared, which is the same as x to the negative 2. So that's going to be a negative 2 over x cubed. And feel free to turn that into an x to the negative 2 to make your life easier, if that makes more sense. Log base 10 of sine x, so this derivative is going to be 1 over x, which is sine x in this case, times the natural log of 10, times the derivative of the inside, which is cosine of x. This next one, we're going to have to do an implicit derivative. Okay, so dy dx is equal to 1 over x tangent y times the derivative of x tangent y, which is a product. So we're going to have x prime tangent y plus the derivative of tangent y times x. So derivative of x is 1, so we get tangent y plus derivative of tangent y is going to be secant squared y. We're taking the derivative with respect to x, so this is going to be times dy dx times x. Now we need to solve for dy dx. So I'm going to multiply this through. So we're going to have 1 over x tangent x times tangent, which is just going to be 1 over x. And then I'm going to have x secant squared y over x tangent y times dy dx. So next I'm going to move this over to this side. So we're going to have dy dx minus, and the x's do reduce. And you can reduce these trig functions. I'm going to leave them like that for now. But you'll notice if you look at the PDF notes, I did simplify it, but you don't have to. Okay, all of that equals the 1 over x. So now I can factor. And then divide. It's going to be ugly, and you can simplify it if you so choose, but I'm just going to leave it as 1 over x over 1 minus secant squared y tangent y. Okay, again, at first glance, this looks awful, right? We've got square roots, we're going to have a product, a quotient, all sorts of things here. So really what I'm going to do is, again, use the fact that this is logs to use the properties. So I'm going to do this in stages. So first I'm going to apply the quotient rule. So y is equal to natural log of the top, so root x cubed root x plus 1 minus the log of the bottom Okay, then I can do products for each of these. So the product here, this is going to be natural log, and I'm going to rewrite this x square root of x as x to the 1/2 plus natural log of x to the 1/3 minus, this is going to be a product, but this minus will distribute. So natural log of sine of x, it would be plus, but we'll distribute, so minus natural log of secant of x. One more step before I actually take the derivative is to bring down these powers. So 1/2 natural log x plus 1/3 natural log of x minus natural log of sine x minus natural log of secant x. Now I will take the derivative. So we're going to have 1/2 times 1 over x plus 1/3 times 1 over x minus 1 over sine of x times the derivative of sine of x, which is cosine, minus 1 over secant of x times the derivative of secant, which is secant tangent. And you can leave it like that. I'm going to go ahead and simplify it a little bit. So this is going to be 1 over 2x plus 1 over 3x. This is cosine over sine, so that's going to be minus a cotangent x. The secants here cancel, so I'm left with 1 over tangent. Or just, sorry, tangent. Just tangent. So using the properties makes life a whole lot easier. Which leads us to the next idea of something called logarithmic differentiation. Okay, this whole mess looks like the ugly mess that we just dealt with, but it does not have a natural log. but wouldn't it be nice if there was, because then we could split this all down. So let's make it natural log, but we have to do it to both sides. Okay, so I take the natural log of both sides. Now I'm going to do the same thing that I just did. So we have a quotient here, so it's going to be the natural log of the top minus the natural log of the bottom. Then we have the product and we have the powers. So I'm going to do that all in one step. If that's too much, then do it step by step, but your result will look the same as mine. So natural log of y equals, the first one is going to be 2/3 natural log x cubed minus 4 plus 1/2 natural log x squared minus 1 minus, now we're on the bottom, 5 natural log x squared plus 3 minus natural log x squared minus 3x plus 5. So now we can do these derivatives quite easily. So we're going to take the derivative of both sides. So the derivative of natural log of y is 1 over y, but we're taking this with respect to y. So dy dx, so 1 over y times dy dx equals, okay, we're going to have 2/3 times 1 over x cubed minus 4 times the derivative of x cubed minus 4, which is 3x, plus 1/2 times 1 over x squared minus 1 times the derivative of that, which is 2x, minus 5 1 over x squared plus 3 times the derivative of that, minus 1 over x squared minus 3x plus 5 times derivative of that, 2x minus 3. Now here's the trick. I want just an expression for dy dx. So to do that, I'm going to multiply by y. Y is this whole thing. So I multiply both sides of this equation by y, but y is really x cubed minus 4 to the 2/3 square root of x squared minus 1 over x squared plus 3 to the 5th x squared minus 3x plus 5 times all of this. So I'm going to have, and you can simplify it in different ways. So we're going to have 2 times 3x squared would be 6x squared all over 3x cubed minus 12. Here, the 1/2 and the 2 cancel, so I'm just left with that x over x squared minus 1. Yeah, I didn't mean to put a parentheses there. So this plus this. Here, I'm going to have minus 10x over x squared plus 3 minus 2x minus 3 over x squared minus 3x plus 5, close parentheses. So that's the derivative of all of that times y to get rid of that. To do this derivative, I'm going to, again, use the quotient rule. So we're going to have natural log of 1 minus natural log of 1 minus x. Well, natural log of 1 is just 0. So really we have natural log of 1 minus x that I'm taking the derivative of. So that's going to be a negative 1 over 1 minus x times the derivative of that, which is a negative 1. So the negatives cancel. So we just have 1 over 1 minus x. Find our correct answer is A. And that's how we take the derivatives of logarithms.